All right. Hello, everyone. Thank you so much for being here. My name is Beth Hood. I'm the Executive Director for Industry and Research Relations for the Cockrell School of Engineering. Thanks so much to our organizers and everyone for making this event happen and for our audience participation. This has been a great showcase of all the research that not only our faculty are doing, but our formal projects and thought partnerships with our external collaborators. And our next speaker, Santiago Miret, is a great example of just that. He is an AI research lead at Intel Labs, focusing on applying AI for scientific problems with an emphasis on material discovery and understanding. His talk today is about just that. But he leads a variety of research efforts across Intel Labs, spanning various research and other academic institutions in North America, Europe, and Asia. He was also the primary organizer for the first AI for Accelerated Materials Design workshop at NERPS 2022 and subsequent workshops there. So I'll kick it over to Santiago to take the lead. Thanks.
Thanks. So as the last person, I hope to at least talk about something interesting. I know it's going to be different because I've seen everybody else talk, but hopefully it will also be interesting. So I wanted to start off with the why, right? So why even try to do AI for materials discovery? And since I work, at a semiconductor company that also does fabrication, sustainability is one of the main motivations. And sustainability kind of motivates new materials discovery in a variety of different ways. The first one that is kind of natural is emissions. Even already a couple of years ago, fabs started to exceed the emission profiles of car manufacturers. So if you think of high intensity manufacturing in terms of energy consumption, in terms of carbon emissions, in terms of water footprint, all of those things are coming together in terms of new fabs, whether they're Intel, whether they're TSMC, or whether they're Samsung. This footprint is only going to continue to grow, so it's going to be important to think of new ways to mitigate this footprint. Another one is the removal of toxic chemicals. And one particular class of chemicals that has gotten attention recently is called PFAS, so fluorinated carbon chains. So these are also called forever chemicals. They were the ones that were used in the Teflon line, and they've gotten infamous because they're forever in the environment, forever in the human body, forever in organic systems, which then leads to bad things, cancer and stuff of that sort. So they're getting phased out, and they are part of the semiconductor manufacturing pipeline still today. So that requires new materials, which means that we need to discover them. From the research perspective, this also presents an interesting opportunity, because if we look at if we do a quick back of the envelope calculation in terms of what might be possible in terms of atomic arrangements and kind of the materials that we've made today, it's easily less than 1%. So that means that this is a very unexplored space, and it's one that I consider to be very exciting. In terms of other opportunities for AI to intersect with materials discovery, it's about accelerated evaluation. I'll talk about how evaluation, even today in simulation, is still very expensive. So this kind of lends itself to a whole class of machine learning methods that can help us accelerate this evaluation. And we can also put tools in the hands of scientists to accelerate the discovery process. So the way that we think about this at Intel Labs is across these 4 different components. So we have an engineering component that is about building new tools. We have a scientific component that excites us as researchers, where we ask, what are the most impactful questions that we want to tackle? Then we have an ecosystem aspect. This is where we work with academics and academic institutions like this one, but also many others. You can see some of the logos here, to really work together to tackle these big questions in an open science approach. And then we have value capture, which is corporate speak for making money in different ways. Like I talked about the manufacturing angle, but in the future, hopefully at some point in time, there is also a hardware angle, right? Everybody knows that NVIDIA has captured all of the value that is from hardware sales related to deep learning, and Intel has not. But there is efforts to try to change that. As part of the ecosystem development, as Beth mentioned, we've been working on a series of workshops. Since this is a new field, we believe that, as I mentioned, we need to kind of work together to address these questions. And AI for Math has been a community gathering forum for many of us. The next one is going to be in Singapore at ICLR. So we hope to see you there, if you have already submitted especially, or if you just want to come check it out, I encourage you to come. it's fundamentally based on three guiding questions. The first one is, what is it that we should make? So this comes at the core of what design is. Like, give me a blueprint for a material that then I can use for whatever application that I care about. Then after that, with materials especially, you have two additional problems beyond design. So even if you have a blueprint, you need to think of how to make it. And this one is a very complex and often underappreciated challenge, because in materials, you don't have a single synthesis platform that can make everything. You need a variety of different techniques to make a variety of different things. Semiconductors are made differently than like biomaterials and ceramics, and so there is like a big challenge here. And after that, you have characterization. So when you actually make something, most of the time you do not get out what you think you want, what you think you will get out when you start that process. And characterization is all about trying to understand what it is that you're looking at. For ICLR specifically, we have a track on multimodal materials design. And for those of you who care about publishing, there is like a focus issue with IOP, who runs Science Magazine. So this is my intro. And the next thing that I'm going to do is I'm going to talk about two research area focuses. The first one is going to be on machine learning interatomic potentials, and the second one is going to be on LLMs as they apply specifically to material science. All right, so machine learning interatomic potentials, or in catchy language, what we want to do is we want to accelerate scientific computing by more than 100x. And the reason for that is, if you look at quantum mechanics, kind of like at a fundamental level, we have something called the Schrödinger equation that describes the behavior of electrons. That is very hard to solve. We haven't been able to solve it for 100 years. So we invented approximations. One approximation is called DFT, or density functional theory. That's the first letters that you see. Even that approximation is not good enough, but we won't talk about that. We'll talk about the fact that it's still too expensive. So that means that we have an inability to like solve this equation. Like, in fact, this is the scaling behavior for DFT. We see scaling behavior of n cubed. For a couple of other approximations, we see n to the 1.6. But if we could train a machine learning model, we essentially have O of n scaling, and in some cases even like O of 1 scaling, because it's just one inference call. And the ability to solve this is very important for electronics, or anything that relates to electronics. So this is renewable energy, semiconductors, fabrication, atoms moving around in space, all types of different things. One thing to keep in mind with DFT, which is kind of like a lesson that many machine learning individuals are relearning, is that it's not a perfect solution, which is what I mentioned earlier. So the approximations that were meant in DFT, they don't capture all materials across the periodic table, but they're kind of like good enough to do many different things. So in order to think about how to even start building models for these kind of use case, the first thing that we need to put together is like a set of tools and a set of data. So that's what we did with the Open MathSciML Toolkit, which is an open source library that we maintain at Intel Labs. We aggregated all of the publicly available data sets that relate to materials, and we built essentially a toolkit that allows you to train and deploy an inference using any hardware platform. We were the first to deploy a materials generative diffusion model on Intel CPUs and GPUs, which made our internal partners happy. So feel free to look at the toolkit and hope that you find utility for it. So now that we have data and we have engineering tools, we have kind of like the plumbing in place. What are the architectures that we're talking about? And fundamentally, the architectures, most of the time when we talk about materials, they're called geometric deep learning, because they deal with geometries in the real world. Generally, when you deal with materials and geometries in the real world, but especially with materials, there's a couple of like symmetries that you need to consider. So this is, you can think of it as an inductive bias. You have invariance, which means that if you move something in space, it doesn't change. Like, invariance in the image domain might be a dog is still a dog, whether it's at the top of the picture or the bottom of the picture. In the case of materials, energy is an invariant quantity. The energy of a material is the same no matter where in space it is. Then you have equivariance, where equivariance is that the transformation happens as you apply the same function. So forces are an equivariant quantity. If I rotate my material 90 degrees, the forces will rotate 90 degrees. Here you see a whole bunch of like different approaches that have been proposed, for invariant, for equivariant, for a bunch of like different approaches, as well as some unconstrained and some of the tasks that people have trained them on. Things like property prediction, dynamic simulation that I'll talk about later, generation, as well as like structure prediction in the case of proteins and AlphaFold. So we have these models, but in many cases, they're not necessarily fast enough or they're not necessarily efficient. So there's a couple of ways that we can think of making them even faster. And the first one that I wanted to mention is called, FAST. So physics over scalable task-specific GNNs. This is a collaboration with Mila. So here, the main insight is that we can take, in the case of a catalytic system where you have an absorbent, so catalytic systems have a molecular absorbent that's kind of above a surface, and then there's a bulk material. This is every car has a catalytic converter, but this is like important if you want to do things like carbon capture, direct air capture. It's kind of like an important thing to consider. So the hypothesis was there's a whole bunch of like bulk materials at the bottom. Maybe they're not as important, or maybe we can model this more efficiently, which is what we did. We took the bulk material, approximated it with one supernode, and long story short, basically the result is we can get the same type of like modeling performance, same error, but at 5 to 10x, the compute acceleration for both training and inference. And at the time, this made it actually competitive to like train some of these models even on CPUs because of this acceleration. So this is one form of acceleration where we look at like the data structure, and we also look at essentially what it is that's necessary and are able to improve that. Another way to do acceleration is to look at the kernel level. So I mentioned equivariance before. The way that most architectures today achieve equivariance is by using something that are called spherical harmonics. So spherical harmonics, if you know what a Fourier transformation is, or if you know what any mathematical transformation is, spherical harmonics are basically a space where, as long as you operate in the spherical harmonic space, you are guaranteed to have certain types of symmetries. And the higher up the order you go in these spherical harmonics, the better your symmetry coverage is. Problem is that these are expensive. And the main library that was implementing spherical harmonics, it was written in Python. So we came in and we thought, okay, can we do this in Triton, where if you're familiar with Triton, it's basically an open source alternative to CUDA. It works on any GPU platform, whether it's NVIDIA, AMD, or Intel. And we implemented these kernels, and we got a lot of acceleration, especially with like higher order of spherical harmonics. So L is the number of spherical harmonics. So L equals 4 is this fourth row up here. And it was able to unblock essentially the access to these higher levels of spherical harmonics compared to what was before, and that enabled us to also do like an explainable study. Another way to think of acceleration is kind of in a data-centric way. And this is where FANET comes in, or frame averaging equivariant networks. So here we're saying, okay, like a lot of architectures put in the equivariance and the symmetry preserving aspects into the neural network design itself. Can we do that via data augmentation? And the answer is yes. The way that you do that is with a concept called frame averaging. So frame averaging essentially stipulates that if you want to get certain levels of symmetry, all that you need is to find the canonical frames depending on what level of symmetry that you want. In the case of equivariance, those ended up being 8 frames. So then if you look at the process here, right, so like we also did like stochastic averaging of this to even, do less than 8 frames, but you get those frames, then you create the graph based off of those frames. And once you have that, you don't need to do like any kind of like fancy math in your architecture. You can just very quickly like pass through it. And what FANET ended up doing, similar to FAST, is that it achieved the same modeling performance as the state-of-the-art methods, but also with like 5x faster compute. Okay, so we've covered some initial architectures, we covered some initial problem settings. The next thing that I want to show is kind of like where some of the challenges lie. So most of the MLIPs today have been trained on publicly available data sets of ideal materials, because that's just the way that the system has evolved. Essentially, when computationalists first started, they wanted to make sure that they could benchmark against experimental results, which are then usually like perfect crystal structures, but perfect crystal structures are not necessarily what's interesting to application. Dopants are defects that you intentionally put inside a material to manipulate a property. They're very important for semiconductor materials. They're essentially what make a PN junction work, which is then the basis of any transistor architecture. So what we wanted to do is we wanted to see if the machine learning potentials that are out in the open literature can essentially handle dopants, and the answer is no. So we have like some analysis to show that in different ways, like we have errors, but I think the most interesting way to look at it is in the embedding space. So these are two different embedding spaces. One is t-SNE, the other one is FATE. So in t-SNE, you can see that the clusters of the dopants are kind of separate from the two major data sets, one being Materials Project and the other one being OMAD that came out of Meta. And in the FATE embeddings, what's interesting about the FATE embeddings is that you have both local and global structure. So the distance actually means something in these pictures. So some dope materials are closer in distance to the structures that are undoped and some are not. So this kind of like gives you a sense based on the model that you're using to generate this embeddings, which in this case was one of the most popular ones called Maze, like how out of distribution the dopants actually are. And this is a significant result because like before we didn't have the ability to just kind of think of that. And just to give you a sense like how these things are generated, basically you take a base crystal structure and then you do a substitution. So you take one of the elements that you want to put in, maybe because you want to increase or decrease the conductivity, and you just substitute it in. And we did that a bunch of times, generate a bunch of data, and that's how we ended up generating the embeddings. So this is like one shortcoming that we found. The other one was, or is related to simulations. So we took all of these like machine learning interatomic potentials. You can see 6 of the more popular ones here, and we plugged them into what are called molecular dynamic simulations, which are essentially a way for molecular dynamic simulations. What you do is you predict forces, and then you evolve the atomic positions based on those forces. There is all types of like heuristic methods that have been developed over the past 30 years that kind of like do things relatively well, but machine learning potentials in theory could provide broadly generalizable potentials. In theory, because all our results show that they essentially don't work on any system that is not within distribution of the training set. That's the takeaway from this, where here you see different error accumulations for essentially density, which all that you need to be able to kind of like get the density right is to keep the atoms in the place where they should be, but all of them fail. So this is like a shortcoming that we pointed out in this study. So there's still a lot of work to do in getting these machine learning techniques towards being useful for materials discovery, even though we've made a lot of progress in like having property prediction models, in also having generative models and many other things. So this is machine learning interatomic potentials. The next thing is LLMs. So we've talked a lot about LLMs, but just to, we talked a lot about LLMs, but just to kind of like set the stage, there is, all of this explosion that has happened, and most people today work in the decoder only space. But if we think about material science, there is essentially 2 sides of the challenge as we see it. One is knowledge acquisition, which means what is the set of knowledge in textual format that is relevant for material science. One is that the text for materials is different than the text in general language to some extent, right? That one is kind of like potentially just like a more data or a fine-tuning problem, as I'll show. But there's also like other types of interesting challenges that occur. When you have structural descriptions, chemical formulas, data in tables, data in figures, all of these different things that maybe you don't find when you're looking at general language, you find yourself in a new setting where you need to process all of that to be able to think about what's going on inside a material system. So you're dealing with structure and properties, you're dealing also with synthesis procedures, analysis procedures. So that's on the knowledge side. The science acceleration side talks about what are the tasks that we need to solve to actually deploy LLMs into materials discovery processes effectively. Question answering is nice, it's useful. It helps with literature review, it helps, potentially with education. But really where a lot of the promise lie is in the ability to execute experiments and the ability to execute experiments automatically. This is where hypothesis generation comes in. So can an LLM generate a scientific hypothesis and create an experiment to either prove or disprove that hypothesis? In terms of interfaces, many machines have, hardware on them that allows them to run all of the control systems that they need to run to control that machine. Each of those has like a computer language that interfaces with them and with each other. Given that, language models ostensibly know all types of languages, can they provide an interface such that humans don't have to think about the interfaces between all of these different machines? So the left side, we've made some progress on. I'll talk about that. The right side, we haven't, which is kind of where a lot of the opportunity lies. So let's talk a little bit about, how do we get material science content into language models. So here, this is a work called Honeybee, where we did basically instruction-based fine-tuning to train a material science language model. So we generated instructions from one of the commercial OpenAI models. These instructions were then verified by an Anthropic model. Then we have a set of instructions that are verified, by the other LLM. These then provide the instruction fine-tuning set, and afterwards, the output of the Honeybee model is evaluated by another independent LLM, and then we can go through this process multiple times through different stages, and what we end up is essentially a model that in different stages is fine-tuned for following material science specific, instructions. So then with instruction fine-tuning at each stage, we improve the performance. And when we benchmark it on the material science language data set, what we essentially find is that the Honeybee model basically gets the same zero-shot performance on these material science questions as like GPT-4, but with at least 10x less parameters. We don't know what GPT-4's parameter count is, but the highest we went was 13 billion, so we think it's safe to assume that it was at least 10x. Okay, so we have essentially a way to do basically PEFT fine-tuning to get a lot of the domain-specific knowledge in. The next thing that we asked ourselves is can we create an agent, right? And rely on, essentially in-context learning as well as tool calling to solve similar types of questions. This is where we end up at Honeycomb. So in Honeycomb, it's an agentic framework. You have a knowledge base, you have a tool hub, you have also, retrievers and processes for choosing the tools or for choosing what to retrieve to basically answer a query. And then the key study that we did for Honeycomb is to think about, is it agnostic and does it improve the performance basically based off of like any model that we plug it into? So in this table, you see different language models that we tried to have as like the main chat model and what it does with Honeycomb. And for almost all of them, augmenting, an underlying language model with Honeycomb improves the performance on material science benchmarks. So these, as well as like general scientific benchmarks. These were questions that were proposed in one case from graduate exams in India, and in other cases for other like also PhD level scientific questions. Okay, so far we've covered, instruction fine-tuning, we've covered agentic behavior with like retriever augmented generations and similar types of flavors of in-context learning. The next thing we thought about is, can we just kind of put it all together and create like a comprehensive language model for material science? And that's what LLaMAT is. So like LLaMAT tries to put together all of these different insights and create essentially a model that can do like many of the tasks in the academic benchmarks that we care about. In order to arrive at LLaMAT, we did three things in sequence. The first one is continued pre-training with like manually curated data set that focuses heavily on publications, but also community forum discussions, CIF files, crystal information files, which are essentially a textual way to characterize a crystal, but also keep a little bit of general language with red pyjama to avoid catastrophic forgetting. After that initial stage, you do general instruction fine-tuning, and then you do fine-tuning to end up either at a chat model or at a generative model for crystal structure generation. So a couple of interesting things in addition to the ability to do this came out of this study. The first one is what we call adaptation rigidity, where we found out that if we use Llama 2 as a base model, we actually get better results compared to Llama 3. Our hypothesis is that Llama 3 was trained on a way larger corpus, and therefore, like when you're thinking about what it means to do fine-tuning, in many ways, it might be easier to push Llama 3 out of the manifold that it's been trained towards compared to Llama 2, which might be a bit more flexible. Another thing that we saw, and I'll show in the results, is that the LLaMAT models essentially outperform out of the box almost all commercial and open source language models on material science specific tasks. So this is the first set of results. So, all types of benchmarking. You have a spider plot where in the spider plot, you want to cover as much area as possible. And what we see is that with Llama, essentially, that's the one that covers the most area. So here we have entity recognition, classification, and extraction. And extraction is one that I think is particularly interesting and important because of what I mentioned earlier. So if you assume that material science knowledge is contained in academic papers, in an academic paper, you have all types of different things, chemical formulas, figures, tables, all types of other information that you don't necessarily deal with in general language. And then what you need to do is you need to extract that information into a useful format. The number of material science publications has also exploded, so this becomes more relevant. So in order to gain access to all of this knowledge, you need to have an effective extraction pipeline. This is what the Llama series of models starts to provide with this. So with the Llama series of models, we can start to use essentially language models to extract the data to then do all types of useful things with it. So this is particularly exciting for many of us that have tried to kind of get our hands on this extraction problem for a while. So this is all well and good. So LLMs are great. They can also help material science. But what is it that LLMs cannot do? So that's a question that we asked with this MATTEX benchmark. So in MATTEX, what we try to do is we try to ask the question if we can use text-based modeling to basically do property prediction on crystal structures. So we sourced a whole bunch of crystal structures, put them in textual formats across 9 different representations with different inductive biases. So you can see the biases here. The biases in the representation essentially expose different kinds of information. So composition is a common way to represent the material. So salt is NaCl, for example. But you can expose also bonding information, symmetries, coarse graining, as well as periodicity. And to cover as much space as we possibly could, we came up with these 9 representations, some of which we proposed ourselves, and some of which were out in the open literature. So we have all of these representations across all of these materials classes. Then we can do a scaling analysis as well, and look at a whole bunch of different things. Long story short, language models suck at modeling geometry. You can parse the table to try to convince yourself of that. But what I recommend looking at is this right side, where here is we made essentially a hypothetical use case. We created a hypothetical potential where we have essentially an energy term that is dependent on composition and it is dependent on geometry, and we have an alpha parameter to vary the dependency, essentially. So this is essentially a use case where in one extreme we have only compositional dependence on one property, and in the other side we have only geometrical dependence on one property, and we benchmark all of the representations against a simple n-gram model. And what we find is that if it's only dependent on composition, then all is well and good. You can model that very well with essentially your transformer architecture. But if the more geometry you put in, the worse it gets. So our hypothesis is that this is kind of a shortcoming of the transformer architecture in terms of being able to include geometric information in an effective way. So that might mean that you might not be able to do everything with an LLM, but there's other things that you can do, right? You can make a better architecture, a tool that you can then call with your favorite tool calling agent. So I'll end with kind of this picture again, because it kind of puts into context what it is that we're thinking about doing next. And it's really about focusing on this right side. So how is it that we can enable essentially the process of executing scientific experiments for materials discovery using language models? And for me, the exciting part is really on the hypothesis generation, as well as finding ways to automate all types of experimental tasks, whether it's running simulations, whether it's actually running a synthesis procedure or automating data analysis. And I think yeah, I'm okay with time still, so I'm happy to take any questions.
And we have time for questions.
You mentioned testing and also processes for formulating these things. but most of the talk is about like coming up with, I feel like, compositions of materials or that kind of thing. Is there any more that you can expand on the later parts of the process, like testing or preparing materials?
So you can do two types of testing. The first one is you can do in silico testing, where you essentially run a simulation to calculate a property or to understand kind of what is happening. If you look at the benchmarks that most papers are published on today, those are bad, which is the reason why I kind of presented the results that I presented to kind of make that point. But we've also done work on those kind of things. In terms of putting things into the real world, that is really an open challenge, right? So one of the things that is interesting here is that we talked a lot about robotics. And I think robotics can be an interesting avenue to actually make the process of material synthesis reproducible. In the chemical and physical literature, there is a huge reproducibility problem. And LK99, if you paid attention to that last year, the famous superconductor is kind of emblematic of that, right? So a group came, we have made a room temperature superconductor, which would solve a lot of the world's problems, but then nobody could reproduce it. So my hope is that as we think of robotic platforms, we find a way to kind of make a lot of that more automated and remove a lot of human error, intentional or unintentional, in those processes.
Other questions? All right, let's thank Santiago again.